Welcome to the Explainer. So, let's be real for a second. If you've ever pumped gas into your car, jotted something down with a plastic pen, or, just turned on a stove to cook dinner, you've interacted with hydrocarbons. Today, we're tackling that eternal student question, why do I actually need to know this? We're taking the invisible, microscopic world of carbon and hydrogen and connecting it straight to your daily life. But more importantly for you, we're structuring this as your ultimate exam masterclass. We're going to distill all that dense, complex textbook chemistry into really clear takeaways that you can actually remember when test day rolls around.
All right, here's our game plan for today. We'll kick off with hydrocarbons in daily life, then decode the whole IUPAC and isomerism language. After that, alkane boiling points explained, followed by key hydrocarbon reactions. We'll wrap up the heavy chemistry with the free radical mechanism, and finally touch on aromatics and toxicity.
Okay, Section 1. Hydrocarbons in daily life, from Earth to energy. Let's get right into it.
So check out this incredible journey from deep underground right to the palm of your hand. We extract raw crude oil straight from the Earth's crust, right? Then it goes through this massive process called fractional distillation. Basically, it separates everything out by boiling point, which gives us our everyday domestic and transport fuels, stuff like petrol, diesel, and kerosene. But the story absolutely doesn't stop at just energy. These exact same hydrocarbons are the starting raw materials for industrial polymers. We're talking the polythene in your grocery bags and the polystyrene in your coffee cups. They're even used as solvents for paints and as the fundamental building blocks for life-saving drugs. It's literally everywhere.
Now, you absolutely need to know the difference between these two highly tested acronyms. First up is LPG, or liquefied petroleum gas. Just think of your kitchen or your home heater. This is a domestic fuel. It's highly compressed, and it's super popular because it produces the least pollution among its peers. On the flip side, we have CNG, compressed natural gas. You'll actually find this gas sitting in the upper strata during oil drilling. When we compress it, it becomes an amazing automobile fuel that really helps reduce urban smog. Trust me, distinguishing between these two is an absolute classic exam question, so make sure you lock these definitions in.
Moving on to Section 2, Speaking IUPAC and Isomorphism, the Language of Chemistry.
Okay, let's dive into this. IUPAC naming can look totally intimidating at first glance, but I promise it's really just a logical checklist. Step 1, always hunt down the longest continuous carbon chain. That becomes your parent name. Step 2, number that chain, but make sure you start from the end that's closest to a substituent, any branching group. You want those groups to get the lowest possible numbers. Step 3, when you actually write the name out, list those substituents alphabetically. So ethyl comes before methyl, and you just ignore prefixes like di or tri for the alphabetizing part. And finally, step 4, carbon is tetravalent. It always needs 4 bonds. Just fill in any missing bonds with hydrogen. Quick study tip for you here. Please don't cram these rules the night before the exam. It doesn't work. Instead, just practice drawing and naming one complex molecule a day. It is a total game changer.
Now, a really massive part of naming involves structural isomers. I always think of this like playing with Lego blocks. Imagine I hand you exactly 5 carbon blocks and 12 hydrogen blocks. You could snap them all together into a long, straight wall, or you could get creative and build a branch tower. You've got the exact same number of blocks, so the exact same molecular formula, but because the structure itself changes, the physical properties of the molecule change entirely. It's pretty wild.
Which brings us perfectly into Section 3, alkane boiling points explained, because shape matters.
Okay, look closely at the numbers here, because there is a strict, undeniable trend for the isomers of C5H12. Pentane, which is just a continuous, straight chain, boils at 309.1 Kelvin. But watch what happens as soon as we add a single branch to make 2-methylbutane. The boiling point drops to 301. And when we make it multi-branched, like 2,2-dimethylpropane, it completely plummets down to 282.5 Kelvin. Remember, the chemical formula hasn't changed at all. Literally only the physical shape has.
So why exactly does this happen? Well, imagine that continuous straight chain like 2 flat hands pressing tightly together. You've got maximum surface area contact there, which means you have much stronger van der Waals forces holding those molecules together. Because they're holding on so tight, you need a ton of heat energy to break that grip. But as a molecule becomes highly branched, it bunches up into this compact spherical shape. Now, imagine trying to press 2 tennis balls together. There is very little surface area contact, right? Less contact means weaker intermolecular forces, and that translates to a much lower boiling point. So yeah, in chemistry, shape truly dictates behavior.
All right, shifting gears to Section 4, Key Hydrocarbon Reactions, Making and Breaking Chains.
Before you can even try to predict reactions, you absolutely must memorize the reactivity order for substitution. For the halogens, fluorine is the most reactive, followed by chlorine, then bromine, and finally iodine. And for alkyl groups, a tertiary carbon is more reactive than a secondary, which is more reactive than a primary. Okay, here's a really fun, catchy memory trick to lock this in for test A. Furious cats bite iguanas 3 times, 2 times, 1 time. Furious for fluorine, cats for chlorine, bite for bromine, iguanas for iodine. Say it a few times to yourself. Furious cats bite iguanas. You're definitely not going to forget that one.
Next up, let's talk about building longer chains using the Wurtz reaction. Here is the exact step-by-step sequence you need. You start off with your alkyl halides and treat them with sodium metal. Now, the absolute critical condition here, and they will test you on this, is that it must be done in a dry ethereal solution. It has to be completely free of moisture. The end result? You yield higher alkanes that always contain an even number of carbon atoms. It's actually a brilliant way to see how chemists can literally stitch smaller molecules together to build larger, perfectly symmetrical hydrocarbons.
Now, another really common method for building alkanes is Kolbe's electrolytic method, which is flowcharted out here. You start with an aqueous sodium or potassium salt of a carboxylic acid, and you basically zap it with electrolysis. This causes an acetate ion to form a free radical right at the anode. These radicals then find each other and combine to form, you guessed it, an even carbon alkane. But wait, here is the classic trap question they love to throw on exams. Can you make methane using this method? The answer is a hard no. Methane only has 1 carbon, and remember, these radicals combine to form chains of at least 2 carbons, so don't let them trick you with that on test day.
So if Wurtz and Kolbe are all about building chains up, pyrolysis is all about breaking them down. Also known as cracking, this is the industrial process of heating higher alkanes to incredibly high temperatures until they literally physically shatter into useful, smaller fragments, like lower alkanes and alkenes. And why does this matter to us? Well, this exact real-world process is how we take large kind of clunky molecules like dodecane, which you'd find in kerosene, and crack them into the highly valuable everyday petrol gas that fuels our cars. It's a huge deal economically.
Moving on to Section 5, the free radical mechanism, or as I like to call it, the 3-step dance.
Okay, let's trace this 3-step dance because it's super important. Step 1 is initiation. Imagine UV light zapping a chlorine molecule, splitting it perfectly evenly in a process called homolysis. This creates 2 highly reactive chlorine-free radicals. Then we move to Step 2, propagation. That eager chlorine radical attacks a perfectly stable methane molecule, stealing a hydrogen to form HCl, but leaving behind a methyl radical in its wake. Now, this newly formed radical goes off and attacks another chlorine molecule, and the cycle just repeats and repeats, setting up this massive continuous chain reaction. Finally, we hit Step 3, termination. The reaction only stops when 2 of these wild free radicals happen to bump into each other, consume each other, and form a stable bond. That brings the whole chain reaction to a screeching halt.
Let's wrap up today's heavy chemistry lesson with Section 6, aromatics and toxicity, the rings of risk.
Actually, let's take a quick breather from the hard science for a second and look at this historical quote. So, the structure of benzene, which is a ring of 6 carbons, literally stumped the best chemists in the world for decades. Then, in 1865, a chemist named August Kekle was dozing off by the fire, and he had this crazy dream about atoms forming long rows that twisted around like snakes. Suddenly, one of the snakes grabbed hold of its own tail, whirling around right in front of him. He woke up with this massive flash of insight. The carbon chain in benzene closes in on itself to form a ring. That one dream literally solved one of the greatest mysteries in organic chemistry history. How cool is that?
But we have to acknowledge that these beautiful, elegant rings have a pretty dark side. Aromatic hydrocarbons, specifically the polynuclear ones that contain more than 2 fused benzene rings, are highly toxic. They're primarily created through the incomplete combustion of organic materials, so think about burning tobacco, coal, or petroleum fuels. When these specific compounds enter the human body, they undergo biochemical reactions that can directly damage our DNA. This makes them highly carcinogenic, which means they are known to cause cancer. It is a really stark reminder that the very chemicals powering our modern lives also carry profound health and environmental impacts.
Which really leaves us with a critical, pressing question. You've seen exactly how these hydrocarbons are structured, you know how they react, and you've seen how deeply embedded they are in literally every single product we touch, from the gas in our cars to the plastic in our everyday devices. But given their proven toxicity and the serious environmental toll they take when burned, how on earth do we balance our immense daily reliance on them as energy sources while still protecting our health and our planet? Honestly, it's the ultimate chemistry problem of our generation. But hey, now you have the foundational knowledge to truly understand it. So keep studying, keep asking those big questions, and I'll see you in the next explainer.